Hey there, welcome back to the channel. So I am back after a long time, and it's been a bit difficult to manage time because I have new work, and my new work requires me to travel a lot. Not necessarily travel to multiple places and then visiting sites, not that, but just the transit time that I have to go to office and then come from office. It's been difficult because it's a total transit time of around 4 hours to 4 hours 15 minutes. And it's not necessarily also about the hours. You also get tired after work. And this is my first time being like full-fledged, fully employed person instead of an internship. So there are work and there's deadlines and those kind of stuff. So yeah, okay, you know, have a job. But, it's been a journey, but now I can say uh, I have kind of figured out about like how to manage my time. Uh, so yeah, I think also you'll be seeing this video only and only if I'm able to record 5 videos in 5 days, right? That's because I need to understand what kind of consistency levels that I can maintain. So I've tried some other stuff in these months that I'm not uploading. So I haven't touched the previous SPSC project yet. I did do some changes after the latest video. Uh, uh, they are present locally, I think. But other than that, I have tried three different projects. Not three different projects in the sense, but so first thing that I tried was updating a networking stack, but I read about it and it was about applying a research paper, like doing a modification in a existing networking stack. And I tried that and it was okay-ish. I did not fully try that. I don't have the benchmarks to show you what kind of improvement that is. I just tried some basic stuff around it and it did not seem as much fun as I thought it might be. The second thing I tried was like, how about I write a network driver for my own laptop, which has Intel, what do you say? The what's the name? It's a Intel networking thing. It's a very simple driver. But then I looked at the documentation, like what would I have to make, and it's like 500 pages documentation, and I'm like I'm not at all going to make that. It, it might teach me a lot of stuff, and it might be really fun, but it's going to be really time consuming and it won't give me like it's a long term project in something that I'm not really sure of, like if I want to progress my career in that. I know I should be looking at stuff like considering like if it, I shouldn't be making decisions like, okay, this is not aligned to my career. I should be working on that. I should be trying new stuff. I did think about that, but it's just, it did not feel fun. So I did not go ahead with that. Next thing that I tried was um, making some modifications to staging drivers in Linux kernel. Like I first thought like not really sure of how the kernel necessarily works. You know, like I've been using Linux for a while. This is currently Max, it's Unix, but I, I have another laptop which I connect to and use Linux on that. I'm not really sure how an operating system works, you know. Like, I did do the modification in the station driver. It was the station driver was what is the company name? The RTL driver. I don't remember the entire name of it, but it's real tech, I think. Yeah, it was a simple fix. Uh, they had it to do this. So I was like, okay, I have made these changes, and I'm pretty sure like how the driver will work. The driver will be built modularly, and it will be stored somewhere, and then when the driver is detected, it will be called. But I don't know the other parts of the operating system that I want to understand, like how does the scheduler work? How does the networking stack necessarily work? Because, okay, I have a few doubts. When I was reading about networking stack, I have one thing that I want to confirm, but I was just not able to get accurate results from LLMs or other kind of stuff. So I just want to understand this stuff and I'll find it out later. So that is one of the goals. And yeah, the other kind, like what, how other systems work, like I was not really sure. And a person recommended that I should be reading OS 3 Easy Pieces book to understand like operating systems. So they also recommended another book. It's a dinosaur book, but it's really big. But so that like okay, OS 3 just seem to be fun to read because the author is really like uh, it's kind of chill book, cool, and it's not really a big commitment. So it's like not like I have to read this entire book to understand this. No, it's a OS 3 easy pieces. I think there are now four pieces to that: virtualization, concurrency, persistence, and security. I think. So I think I would like to understand virtualization. I might read about concurrency a bit, but I mean I would like to understand how operating systems handle concurrency. Okay. Also, there is one thing in that which one thing in the next piece, which is file system. Okay, I think I should open the. Okay, this goes easier. Okay. I'll open the index itself. Downloads, documents, notes, DB, open. Yep. Yeah. Okay. So this is virtualization, and then there's virtualization. There's concurrency, concurrency problems, email-based, this kind of thing. Yeah, persistence. So in persistence, I have to read about rates, and then I want to read about. Oh, sorry, it was about. Is it inside this? It should open security systems. Yeah, entry file system. I need to read about this because it is something that I have. I this is EFS is something that I use. How can I say? I don't really use it, but the existing systems in my work environment are built on top of it. So I think I would understand this, like read distributed systems, some network NFS, and then EFS maybe. Uh, and yeah, and then there's security, but I don't think it's included over here. But there is. So that's what my goal will be. 8 minutes in, and I haven't really done anything. Okay, cool. So we're going to get started with this. We'll be reading about. I've read some parts of it. I think I've read the first. This is okay. This is the intro. What is this? Hmm. What's that? Wonderful. Why start? Wonderful. Okay. Very slow. zero bytes, so it's not necessarily like it's partially downloaded. Maybe it might be partially downloaded, but then it would have. Okay, I'll look into that later. But okay, I think virtualization. So this is dialogue virtualization. So this must be the professor and the student talking. And then there should be another dialogue. Yeah, dialogue concurrency. So these are like the starting blocks. Okay, VM means virtual memory, right? CPU intro. So I might have read like a few starting stuff. Yeah, I've read them. So I'm going to start from the same stuff because I want to revise stuff. Maybe I might understand something new that I don't know about, but I'm moving into that. Huh. It's going to be all rubbish. Yeah, 300 lines of it. Ooh. Hmm. Yeah. Oh, this is cool. Um, yeah, I think I'm sure. Yeah, should I read this from start? 13 pages, right? It's not necessarily all 13 pages. My 10 pages. Yeah. I think I can do 10 pages. So let's go ahead. So in this chapter, we discuss one of the most fundamental abstractions that the OS provides to the user, the process. The definition of a process informally is quite simple. It is a running program. The program itself is a lifeless thing. It just sits there on the disk, a bunch of instructions and maybe some static data, waiting to spring into action. It is the operating system that takes these bytes and gets them running, transforming the program into something useful. It turns out that one often wants to run more than one program at once. For example, consider your desktop or laptop where you might like to run a web browser, mail program, a game, or music player, and so forth. In fact, a typical system may be seemingly running tens or even hundreds of processes at the same time. Doing so makes the system easy to use, as one never need to be concerned with whether a CPU is available. One simply runs programs. Hence our challenge, the crux of the problem. So how to provide the illusion of many CPUs? Although there are only few physical CPUs available, how can the OS provide an illusion of nearly endless supply of CPUs? Well, that this is quite easy. Uh, I don't think virtualization of the CPU is a hard thing for me to understand. It's quite simple. The hard thing for me to think it's not necessarily hard. You can say, how do I grasp it? The concept of virtualization, right? In terms of CPU, one can easily understand that you stop a process and then let another process run it, and then you stop that one, and then you start the prior process again, and then it's kind of an illusion that uh, many processes are working at the same time, and then they think that we have our own CPU, so that is kind of like virtualizing the CPU. But I don't understand virtualizing the memory concept. I don't understand how do we do that. Like, do we let other processes share a single segment of memory? Because if a process is about to, let's say this is a block of memory, right? If this process wants to use it, and there is another process that will to use it, like virtualization of a memory is showing that a process has a lot of memory. So to show that you have a lot of memory, you need to some way share a single segment of memory, right? And if I were to store, if the first process were to store something on it, and then a second process goes, okay, I want to store something else on it. So how will the first process move this memory to somewhere else? Like, you understand me, right? Because this process can't just override this. This for this process, this is still a virtualized part. This is still their memory, right? And for this process, it is their memory. So, uh, okay, I don't think I'm that good at explaining my doubts. So I'll just read. Okay. This basic technique, known as time sharing, allows user to run as many concurrent processes as they would like. The potential cost is performance. Oh, I did not read this part. Okay. The OS creates this illusion by virtualizing the CPU, by running one process, then stopping it, and then running another, and so forth. The OS can promote the illusion that many virtual CPUs exist, when in fact there is only one physical CPU or few. This basic technique, known as time sharing of the CPU, allows users to run as many concurrent processes as they would like. The potential cost is performance, and each will run more slowly if the CPU must be shared. To implement virtualization of the CPU and to implement it well, the OS will need both some low-level machinery and some high-level interventions. We call the low-level machinery mechanisms. Mechanisms are low-level methods or protocols that implement a detailed piece of functionality. For example, we will learn later how to implement a context switch, which gives the OS the ability to the ability to stop running one program and then start another program on a given CPU. This time sharing mechanism is employed by modern OSs. I think I do remember like how to start a process. Like what all parameters does the CPU need? Like what variable to store on the register and those kind of things. I think that it is covered in the next parts. I do remember it frankly. Like there being a like huge struct or something. Use time sharing and space sharing. Time sharing is a basic technique used by an OS to share a resource by allowing the resource to be used for a little while by one entity and then a little while by another, and so forth. The resource is in question. Sorry, the resource in question, for example, CPU or a network link, can be shared by many. The counterpart of time sharing is space sharing, where a resource is divided in space among those who wish to use it. For example, disk space is naturally a space shared resource. Once a block is assigned to a file, it is normally not assigned to another file until the user deletes storage to file. Yeah, but this is like divided, right? Resources divided in space. Yeah, cool. I want to understand how why do people say like a single process has like infinite memory? I want to understand that. Okay, on top of these mechanisms reside some of the intelligence in the OS in the form of policies. Policies are algorithms for making some kind of decision within the OS. For example, given a number of possible programs to run on a CPU, which program should the OS run? A scheduling policy is the OS will make this scheduling policy in the OS will make this decision. Will make this decision likely using historical information. Example, which program has run more over the last minute, workload knowledge, what types of programs are run, and performance metrics. That is a system optimizing for interactive performance or throughput to make its decision. Okay, cool. I understand that sharing policy, and yeah, I think eventually we will learn about it. Do processes carry like flags that say like, oh, I'm an important process? Because there is a thing called priority, right? Priority scheduling. So you never know, there might be, If I were to design a system, I think I would add something like the flags, like higher the number, higher the priority, and those kind of things. Yeah. Do current systems have it though? Not really sure. Or do they just analyze like how much time a process has taken, or something like system optimizing for internet performance or throughput, like they want latency or throughput, those kind of things. The abstraction, the process. The abstraction provided by the OS of running program is something we will call a process. As we said above, a process is simply a running program. At an instant in time, we can summarize the process by taking an inventory of the different pieces of the system it accesses or affects during the course of its execution. To understand what constitutes a process, we thus have to understand its machine state, what a program can read or update when it is running, at any given time what parts of the machine are important to the execution of the program. One obvious component of machine state that comprises a process is its memory. Instructions lie in memory. The data that the running program reads and writes sits in memory as well. Cool. Thus the memory that the process can address, thus the memory that the process can address is part of the process. Is the memory that the process can address is part of the process. Yeah, cool. Understandable. Also part of the process is machine state are registers. Oh, I think we might not be able to read this. Should I? Okay, so this is half part of our screen, right? So this is half. Yeah, okay. So this is half. So if I were to read this, you might understand this. And this is not one third, but yeah, let's consider one third of my screen. So this is one third of my screen. Taken. So this, okay, cool. So I need to read it like this, where the text is in the center. Okay, for you to be able to read it, look at it as I'm reading. Okay. Also part of the process machine state are registers. Many instructions explicitly read or update registers, and thus clearly they are important to the execution of the process. Okay. Uh, so process machine state and registers. Yeah, cool. As I said, the instructions have registers like move 2 into EAX or RAX register, whatever that thing is. I think I should understand assembly. I did have a course and did a little bit of assembly, ASM. Oh, sorry, not ASM, the TASM. What's that called? As in, whatever the thing was. I don't remember. But it was fun, so maybe I should try assembly again. Okay. There are some particular special registers that form part of this machine state. For example, the program counter, PC, sometimes called the instruction pointer, or IP, tells which instruction of the program will execute next. Similarly, a stack pointer and associated frame pointer, yeah, are used to manage the stack for functional parameters, local variables, and return addresses. I do know what a program counter and instruction pointer is. I think they are the same thing. Instruction pointer is basically a single number is that points to the next instruction that needs to be taken up. So let's say instruction pointer is X. Let's say the current instruction that is running is X, then the instruction pointer will have the value X plus 1 so as to point to the next instruction that needs to be loaded and needs to be executed. And then when that instruction is loaded, the instruction pointer is incremented. Basically that. I don't know what a stack pointer is. Stack pointer should be the top of the stack, right? Right? For the instruction of the program will execute similarly a stack pointer and associated frame pointer are used to manage the stack function parameters. What is a frame pointer though? We have time. We are currently on page 3. I don't think we have time. But let's keep that in mind. Let me write it down somewhere. How about that? Just give me a minute. So I will read it off camera, or maybe if I have time, I'll read it on camera. You know. Um, Surprisingly, I haven't lost the marker which I had because I always keep it with me. I do need to clean the whiteboard a bit. I remember the old days, like not necessarily old days, but that time when I was working on uh, memory allocator. Ah, that those were good days. That was a lot of fun designing the memory allocator on the whiteboard and then rewriting it every week. Oh my God. it was a fun time. That was the golden era of Jiu-Jitsu, right? That was the peak Jiu-Jitsu. I had a domain. Okay, I need to clean the whiteboard and stuff. Okay. Uh, till then I'll talk about the golden era. That was a fun time. Like, I was really having fun. I was looking forward to every single day. Like I used to get up and I was like, yo, what if what if I do this? Like not I won't think of in a dream, but it's just like I would wake up and I was like, oh, okay. I used to have new thoughts. Most of them were pretty bad. So yeah, but then like I used to get a bit clearer thoughts afterwards, and then I used to rewrite stuff, better design. I used to read stuff. That was a lot of fun. The thing is, I had a lot of time too, right? And that moment, I had college, but I did not used to attend it because colleges don't really teach you that much. At least the Indian ones. The Indian colleges are trash. The teachers are trash too. It's not like they are bad and they are egotistic. But there are some good teachers, and you won't really find them as easily as you would the bad ones. The bad ones are very, very common, and they are increasing in number that I've heard. Okay, so yeah, what was I going to try? Yeah, stack pointer and frame pointer, right? And the marker doesn't have it. And the marker has a ink. Let's go. We are so bad. I should even write down the page number, right? Uh, three. Let's actually do. And okay, frame pointer are used to manage the stack for function parameters, local variables, and return addresses. Finally, programs often access persistent storage devices too. Such I/O information might include a list of the files the process currently has open. Okay, a list of files the process currently has open. Okay. Yeah, I remember the file IO, like I think uh, storing the file descriptor, I think. Whatever. I think it's covered in the next part, next coming part, maybe in the later parts, like down the line. In many operating systems, a common design paradigm is to separate high-level policies from the low-level mechanisms. You can think of the mechanism as providing the answer to a how question about a system. For example, how does an operating system perform the context switch? The policy provides the answer to a which question. For example, which process should the operating system run right now? Separating the two allows one easily to change policies without having to read through the mechanism, and is thus a form of modularity, a general software design principle. Right. We should be separating like policy and mechanisms, right? Mechanisms is how we are going to do it, and policy is which. That's pretty easy to understand. Policies and mechanisms. Yeah. Um, yeah. Cool. Process API. Though we defer discussion of a real process API until a subsequent chapter, here we first give some idea of what must be included must be included in any interface of an operating system. These APIs, in some form, are available on any modern operating system. Also, okay, I would like to tell this. I'd like to let you know this. I'm also reading this book a bit because it's more like, you can say, like me trying to get better at reading. As you see, I fumble a lot, but yeah, I need to get better at that. When the sentences are too long, I am not able to like keep the tone. I go in a monotone kind of way and I mess up the sentences and grammar. So I need to get better at that too. Cool. So, uh, yeah, cool. So there needs to be a create method. An operating system must include some method to create new processes. When you type when you type a command into a shell or double click on an application icon, the OS is invoked to create a new process to run the program you have indicated. Destroy, as there is an interface for process creation, systems also provide an interface to destroy processes forcefully. Of course, many processes will run and just exit by themselves when complete. When they don't, however, the users may wish to kill them, and thus an interface to halt a runaway process is quite useful. Yep, cool, understandable. Wait, sometimes it is useful to wait for a process to stop running. Thus, some kind of waiting interface is often provided. Cool. Miscellaneous control. Other than killing or waiting for a process, there are sometimes other controls that are possible. For example, most operating systems provide some kind of method to suspend a process, stop it from running for a while, and then resume it, continue it running. Then what's the difference between wait and miscellaneous control? I should write it down. Or maybe, yeah, I should write it down. I'll just cover it, if I have time. So this is page number 3. Cool. We are having a lot of doubts. So miscellaneous control. Maybe I should write stuff on this whiteboard, like what do I need to read in miscellaneous control. Status. There are usual interfaces to get some status information about the process as well, such as how long it has run for or what state it is in. Cool. CPU. So we have CPU, memory, code, static data, heap, stack, process. So there is a process. Code static program disk. Loading loading takes on this program, which is this, and reads it into the address space of the process. Cool. So this is the process. We have static code data, other kind of data, and it's loaded into the the memory that is allocated to the process. We do know what does the memory for a process looks like. The stack, heap, the pointers, where the uh, point of there is the break pointer and those kind of stuff. I do remember how I made the movie out. Right, I had invested a lot of time on that. Process creation, a little more detail. One mystery that we should unmask a bit is how programs are transformed into processes. Specifically, how does the OS get a program up and running? And how does the process creation actually work? The first thing that the OS must do to run a program is to load its code in static data, example, initialize variables into memory, into the address space of the process. Programs initially decide on this. Wait, if I want to run a process, I should have that process. Like, okay, if I, so, okay, if let's say I am an operating system, I have my own address space, and if I were to run a process, then I should load that process into my address space, like all the data. What if I want to load another process? So I need to allocate that space myself. But what if I'm not an operating system? Let's say I'm another process, which is a small one, and I load something bigger. I can ask for pages. That's fine, but is this how systems work? Okay. Okay, I'm learning new stuff. I'm forced to think, so that's a good sign. One mystery that we should unmask. Okay, the first thing that the OS must do to run a program is to load its code and any static data, for example, initialize variables, into memory, into the address space of the process. Programs initially reside on disk, or in some modern systems, flash-based SSDs, in some kind of executable format. Cool. Thus, the process of loading a program and starting data into memory requires the OS to read those bytes from disk and place them in memory somewhere. Cool. In early or simple operating systems, the loading process is done eagerly, that is, all at once before running the program. Modern OSs perform the process lazily, that is, by loading pieces of code or data only as they are needed during program execution. To truly understand how lazy loading of pieces of code and data works, you will have to understand more about the machinery of paging and swapping topics. We'll cover in the future when we discuss the virtualization of memory. For now, just remember that before running anything, the OS clearly must do some work to get the important program bits from disk into memory. Cool, understand that part. Once the code and static data are loaded into memory, there are few other things that the OS needs to do before running the process. Some memory must be some memory must be allocated for the program's runtime stack or just stack. Okay. As you should likely and already know, C programs use a stack for local variables, function parameters, and return addresses. The OS allocates this memory and gives it to the process. The OS will also likely initialize the stack with arguments. Specifically, it will fill in the parameters to the main function, that is argument C and argument B array. Okay, should I say that's not that much, isn't it? Cool. The OS may also allocate some memory for the program's heap. In C programs, the heap is used for explicitly requested dynamically allocated data. Programs request such space by calling malloc and free by calling malloc and free it explicitly by calling free. The heap is needed for data structures such as linked list, hash tables, trees, and other interesting data structures. The heap will be small at first as the program runs and requires more memory via malloc library API. Oh, okay. I think I do understand that. We have that data of a process in a different place. That's it. Yeah, that was so easy to understand. Or at least that's how I do it, right? Like if I'm a process, I won't really create the address space for the new process in my address space, right? But then what about an operating system? It can't really operating system itself is a process, right? I need to read about it, but it's getting a bit late. It's not really late, it's 11:41, it's fine. But I need to cover this too. Okay, cool. Please bond and allocate more memory to the process. I should write it down. Let's go very fast. Where does parent process create address space for child? Hmm. So OS will also do some other initialization with the heap will be small at first, the program runs, and request memory. The OS may get involved and allocate more memory to the process to help satisfy such calls. Cool. Okay. The OS will also do some other initialization tasks, particularly as related to input output. For example, in Unix systems, each process by default has three open file descriptors for standard input, output, and error. These descriptors let programs easily read input from the terminal, print output to the screen. We'll learn more about I/O file descriptors and the like in the third part of the book on persistence. Okay, by loading the code and static data into memory by creating and initializing a stack by doing other work as related to I/O setup, the OS has now finally set the stage for program execution. Okay, it thus has one last task to start a program running at the entry point, namely main, by jumping to the main routine. Through a specialized mechanism that we will discuss next chapter, the OS transfers control to the CPU to the newly created process, and thus the program begins its execution. Process states. Okay. Now that we have some idea of what a process is, though we will continue to refine this notion, roughly how it is created, let us talk about the different states a process can be at a given time. The notion that a process can be in one of these states arose in early computer systems. In simplified view, a process can be one of the three states. It might be running. In the running state, the process is running on the processor. This means it is executing instructions. Cool. Ready. In a ready state, a process is ready to run, but for some reason, the OS has chosen not to run at this given moment. Cool. Understandable. And then blocked. In the blocked state, a process has performed some kind of operation that makes it not ready to run. The blocked state, the process has performed some instruction operation that makes it not ready to run until some other event takes place. A common example: when a CPU initiates an I/O request to a disk, it becomes blocked, and thus some other process can use the processor. Cool. If you were to map these states to a graph, uh, if you were to map these states to a graph, you would arrive at figure 4.2. It's this one. So if it's running, it is descheduled, it becomes ready. If it is ready, it becomes scheduled and running. I/O is initiated, then it's blocked. I/O can do your work. The CPU doesn't have to wait for you. And when I/O is done, it goes to ready, and when it's ready, it can become running. Right? Cool. If we were to map this area, as you can see in the diagram, the process can be moved between ready and running states at the discretion of the OS. Being moved from ready to running means process has to be scheduled. Being scheduled, being moved from running to ready means if I move it from running to ready means the process has been descheduled. Once process has become blocked, example by initiating an I/O operation, the OS will keep it as such until some event occurs, example I/O completion. At that point, the process moves to a ready state again and potentially immediately to running again if the OS so decides. Let's look at an example of how two processes might transition through some of these states. Firstly, imagine two processes running, each of which only use the CPU. They do no wait, what? First, imagine two processes running, each of which only uses CPU. They do no I/O. Cool. In this case, a trace of the state of each process might look like this. Okay, so process zero, process one, cool. Running. This is ready. And then when this program ends, now done, running. Cool. This is, yeah, running. And then process one starts running because process zero initiates IO. Process zero is blocked. Cool. So process one runs. And then process one now done. Wait, so IO is done over here. So process zero becomes ready again. But it didn't give control back. It's like, okay, I have two steps remaining. You can run afterwards like a complete, cool. So this is taken up by scheduling policy, right? If process zero might have been like something really important, then process zero will be running right as the IO is done. But it's not because of scheduling policy or something. Right? Cool. In the next example, the first process issues an IO after running for some time. At that point, the process is blocked, giving the other process a chance to run. Figure 4.4 shows a trace of the scenario. Okay. More specifically, process 0 initiates an IO and becomes blocked. Waiting for it to complete, the process become blocked. For example, when reading from a disk or waiting for a packet from a network, the OS recognizes process 0 is not using the CPU and starts running process 1. While process 1 is running, moving, the IO completes, moving process 0 back to ready. Finally, process 1 finishes and process 0 runs and then is done. Note that there are many decisions the OS must take, even in the simple example. First, the system has to decide how to run process 1, while process 0 issued an IO. Doing so improves resource utilization by keeping the CPU busy. Second, the system decided not to switch back to process 0 when its IO completed. Yep, it is not clear if this is a good decision or not. What do you think? These types of decisions are made by the OS scheduler. Cool. The topic we will discuss few chapters in the future. Data structures. The OS is a program, and like any program, it has some key data structures that track various relevant pieces of information. To track the state of each process, for example, the OS likely will keep some kind of process list for all processes that are ready and some additional information to track which process is currently running. Okay, cool. So the OS has a list to track the state of each process, for example. OS will likely did I not find anything interesting in this? Right, yes, yes, yeah. Nothing was that as I guess except for this. Yeah, nothing. I don't think there is anything important in this section. Yeah, okay, cool. Hey, so this is the stuff. Yeah, so, okay, cool. Yeah, I remember that. The OS must also track in some way block processes. When an IO event completes, the OS should make sure to make the current process and ready to run again. Figure 4.5 shows what type of information an OS needs to track about each process in the x86 kernel. What is x86? Similar process. Should I then I will use OS should make sure to read this. Figure 4.5 shows what type of information an OS needs. Okay, to track about each process in the x86 kernel. So this is the registers x86 will save as DC to stop this. These type of decisions are made by the OS user. Yeah, no, not. It's not really. Okay, similar process structures exist in real operating systems such as Linux, Mac OS X, or Windows. Look them up and see how much more complex they are. From the figure, you can see a couple of important pieces of information. The OS tracks about a process. The register context will hold for a stop process the contents of its registers. When a process is stopped, its registers will be saved to this memory location by restoring these registers by storing these registers, the spacing is value back into the actual physical registers, the OS can resume running the process. We'll learn more about this technique known as context switch in future chapters. We can also see from the figure that there are many other states a process can be in beyond running ready and block. Sometimes the system will have initial state that the process is in while it is being created. Also, a process will be in a final state where it has exited but has not been cleaned up in Unix-based systems. This is called a zombie state. The final state can be useful as it allows other processes, usually the parent that created the process, to examine the return code of the process and see if the just finished process executed successfully. Usually, programs return zero in Unix-based systems when they have completed a task successfully and non-zero otherwise. When finished, the parent will make one final call, example wait. When finished, the parent will make one final call, example wait, to wait for the completion of the child. Oh, okay. Oh, fair, fair, fair. Right, right, fair, fair, fair. And also indicate to the OS that it can clean up any relevant data structures that refer to the now extinct process. Okay. So if you look at this structure, that whatever the x86 is, registers x86 will say ERP, ESP, EBX, ECX, EDX, ESI, EDI, EDB. Okay. The different states a process can be in: unused, embryo, sleeping, runnable, running, zombie. Okay. So the position, the function of this starts about the precision going so this context and state. So we have startup process memory, cool. Size of process memory. Okay. Wait, the um, if we have if we have the pointer to the start of the memory that the process that the child process is, so that means it's not really creating the address space for the new process somewhere else. It's in the same user. It's in the same address space of the parent process, right? This has to make sense. This is it. Otherwise, you are like the memory pointer that we receive. I mean, no, it won't be a physical pointer. It will be the pointer of uh, the address space itself. It's the virtual thing. I do need to read about this. Outside integer is Z, size of process memory, cool. Uh, Key stack pointer, bottom of kernel stack for this process, bottom of kernel stack for this process. No, not really sure what that means. Enum, the state, yeah, okay. Uh, Process ID, parent process, okay, struct of parent process. Uh, okay, void is Chan general. If zero sleeping on Chan, okay, not sure. Killed if zero has been killed, okay. Struct file, or the if a file has been opened. Current directory, yep. Switch here to run process, okay. Trap frame for the current interrupt. I'm not sure what that is. You can also see from the figure the things file state. Yep, 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 yep. Okay, cool. So summary, we have introduced most basic abstraction of the OS. The process, it is quite simple. It is quite simply viewed as a running program. With this conceptual view in mind, we will now move on to nitty-gritty, the low-level mechanisms needed to implement processes, and the higher-level policies required to schedule them in an intelligent way. By combining mechanisms and processes, we will build up our understanding of how an operating system virtualizes the CPU. Cool. Yes, the zombie state, just like real zombies, the zombies are relatively easy to kill. But what different techniques are usually recommended? Apache this way. GG. Aside key process terms, a process is a major OS abstraction for any program. At any point in time, the process can be described by its state, the contents of memory in its address space, the contents of CPU registers, including the program counter and stack pointer, among others, and information about I/O, such as open files, which can be read or written. The process API consists of consists of calls programs can make related to processes. Typically, this includes creation, destruction, and other useful calls. Processes exist in one of many different process states, including running, ready to run, and blocked, different events, example getting scheduled or rescheduled or waiting for an to complete transition process from one of these states to another. Cool. A process contains information about all processes in the system. Each entry is found in what is sometimes called a process control block. Okay. A process list contains information about all processes in the system. Each entry is found in what is sometimes called the process control block, which is really just a structure that contains information about the specific process. Okay. I did not read this one. I should have done that. I'm thinking, why do we talk about process control block? Cool. Operating systems can replete are operating systems are replete with various important data structures. I'm just going to assume that replete means filled with, are filled with various important data structures that we will discuss in these notes. The process list, also called the task list, is the first such structure. It is one of the simpler ones, but certainly any OS that has the ability to run multiple programs at once will have something akin to this structure in order to keep track of the running programs in the system. Sometimes people refer to the individual structure that stores information about a process as a process control block, PCB. A fancy way of talking about a C structure that contains information. Body structure also called the process descriptor. Yeah, okay, cool. Yeah, okay. Process control blocks kind of like this. Cool. So these are the references. The x86 operating system by this. The coolest real and little OS in the world. The coolest real and little OS in the world. Rather than play with it, learn more about the details of how operating system actually work. We haven't been using an older version. We have been using an older version, and hence some examples in the book may not match the latest in the source. Okay, we studied the nucleus of multiple governing systems. This paper introduces one of the first important kernels in the operating system called the nucleus. The idea of smaller, more movable systems is a theme that presents itself repeatedly in the course history. The one with the brick and since work described herein multiple applications for Japan's this began to find the early types of concepts around building multiple systems, also has its expression Hydra. The early paper about how to structure operating system research OS known as Hydra. While Hydra never became a mainstream OS, some of its ideas influenced OS designs. This another paper called Multics, which describes. Oh, I have heard about Multics. Another paper on Multics, which described many of the basic ideas that we find in modern systems. Some of the vision behind computing as a utility are finally being realized in modern cloud systems. Okay, so yeah, there will be work. Okay, so this is homework simulation. This program, process1.py, allows you to see how process states change as program run and either use the CPU, example, perform an and out operation, or do I/O, example, send a request to a disk and wait for it to complete. See the README for details. Okay. Um, so I think for that we will have to go for the side. Was these places Wisconsin, Madison, Wisconsin or Wisconsin, Wisconsin. Why do you say Wisconsin? Yeah, Wisconsin, Wisconsin. Yeah, okay. So I think there was a little bit yeah, the projects. So the chapters of homeworks at the end. Okay. Is this it? Precious intro. Yeah. Okay. Cool. Yep. What would go wrong if I have a teacher's head and I'm just going to unzip it? Cool. Let's analyze this. Not analyze this. Fancy way of saying just let's read the code. Which are reagents? Lunch. And dollars. Okay. Yeah. I, okay. Yeah. This notes my documents downloads. Cool. 114 lines. Cool. This program called process.py allows you to see how the state of a process state changes as it runs in CPU and is covered in the chapter. Running, ready, waiting, done. In this homework, we will learn how this process state changes the program. This to run the program and get these options, do this. Okay. If this doesn't work, type Python before the command like this. Uh, okay. I can just what you should see is this usage. Cool. The most important option to understand is the process list as specified by the dash L or dash process list flags, which specifies exactly what each running process program or process will do. A process consists of instruction, and each instruction can just do one of two things. Use the CPU, issue an IO, and wait for it to complete. When a process uses the CPU and there's no IO at all, it should simply alternate between running on the CPU or being ready to run. When process uses CPU and there's no IO at all, it should simply alternate between running and ready. Like cool. For example, here is a simple run that has one program being run, and that program only uses CPU. It does not use IO. Produce a trace of what would happen when you run these processes. Process 0, CPU, 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 CPU. Important behavior systems will switch when the current process is finished or issues an IO of the IOs. 500, which means it should consist of 5 instructions, and the chances that each instruction is a CPU instruction are 100%. Oh, okay, I got it. We can see what happens to the process by using the dash C flag. Okay, this result is not too interesting. The process is simply in the run state and then finishes using the CPU the whole time and thus keeping the CPU busy. Let's make it slightly more complex by running two processes. 500, 500, there are two processes. So ready, run, ready, run, ready, run. Important behavior scheduler will switch between the current process, when the current process is finished and issues an IO after IOs. Issues an IO. After IOs, the process issuing the IO will run later when this is done. Right. So currently they don't have any IO, so they just like run one after another. As you can see about the first process with the process ID or PID, zero runs, while process one is ready to run but just waits until zero is done. When zero is finished, it moves to the done state, while one runs when one finishes, the trace is done. Let's look at one more example before getting to some questions. In this example, the process just issues IO request. We specify here that IO takes 5 time units to complete with the flag dash L. Okay, so 5 is to 100 is 5 instructions and the probability of it being a sequence instructions. Cool. So here 30 means there is 3 instructions and 0 probability of it being a CPU one. So all of them are IO and dash L is what is the time taken by each IO. Okay, so there are 3 instructions, cool, and all of them are IO. Important behavior system will switch between the current process is finished and all issues and IO. After IO is a process issuing the IO will run later when it is stopped. So run IO start. Process ID CPU is waiting, 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 and it's done. Run IO start again. Done, 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 and then this is file done. Cool. As you can see, the program just issues 3 IOs. When each IO is issued, the process moves to a waiting state, and while the device is busy servicing the IO, the CPU is idle. Let's print some stats, run the program as a graph, but with a dash P flag to see some overall behaviors. CPU busy 3. For 3 instructions, CPU was busy, which is the fun parts 1, 2, and 3. And for the remaining 12, which is 4, 3 is 12, was IO busy. Okay. As you can see, the trace took 16 clock ticks to run, but the CPU was only busy less than 20% of the time. The IO device, on the other hand, was quite busy. In general, we would like to keep all the devices busy as that is better users. There are a few other important flags, dash at seed. Dash a seed, the random seed. This gives you a way to create a bunch of different jobs randomly. L, IO length to length. A dash plus, process switch behavior, switch process switch behavior, process switch behavior, then to switch between process switch and IO switch and then. This determines, okay, if I would have added this switch on IO, the system will switch when the process issues an IO. The system will only switch when the current process is done. Dash IO done behavior. Type of behavior when the IO ends, IO run later, IO run immediately. Immediate. This determines when a process runs after its this determines when a process runs after it issues an IO. The process runs after it issues an IO run immediate, IO run immediate, switch to this process right now. Later, switch to this process when it is natural. Okay, depending on process switching. Maybe I'm saying back into that for that. Okay, I think I'm ready to answer the questions. Let's look at the code. Navigator uses okay. Use- okay. 325. So I'm not going to read that because it's not going to be uh, s- real processes being created, right? This has to be like a simple Python program. This, this random says, right, there are no threads to create new process. Create. You don't necessarily, right? Yeah, this is not what. Let me, let me just answer the questions that we have. Run process run by with the following flags. Uh, dash L. Wait, what is dash L? Wait, I don't remember dash L. Oh, process list. Yeah. What should the CPU utilization be? Example: the percent of time the CPU is on use. What do you know? Or why do you know this? Use the dash C and dash P flags to see if you were right. So, uh, this will create two processes, each of five instructions, and 100% CPU instructions. So this will be like 100% utilization for the CPU. Right? That is obvious. Dash bill 500, 500. Oh, that's good. Missing parameters to call print and print. What version of Python is this? Oh my God. Okay, so we just take this and then if I print, then have a space like this, and then how do we represent the words? It's for line 73. If I print this over here, This is simple game. I'm not going to take the time with this, but I do need to run this. 0.7. The other thing is that I don't have Python 2.7, so I just create how I don't have which will this work is not allowed to. Okay, so I can remove them easily. Great. Yeah, how the time really good. Okay, that was available. Unsigned long, unsigned here, yeah, command prototypes. I don't understand that. There is no point in trying to. Oh, okay. What we reverse everything we did and convert the Python to file to Python 3 syntax. Is that it? Okay, I'll also use that. Yeah, with syntax. Something like this slash event AWS plus this something this or what. Okay. Yeah, so I want to look up this. Okay. And then this is, yeah, I'll just modify it and copy it. Wait, what you, okay, it's correct. Yeah. Produces trace. This is. And if I want this, select dash p flag. Wait, does dash p flag need to be added before it? If I do this, if I do this, sorry, use the dash c and dash p flags to see if we overwhelmed. Compute answers for me. Okay, I want to see an example where we use the dash c. Okay, dash c can be added at the end. Oh my god. So dash p print stats. Okay, dash c and dash p. Stats IO busy 0, CPU was busy 100% of the time. That's why I said. Now run with these flags. Dash L 400 and 1 is 0. These stacks specify one process with 4 instructions, all to use the CPU, and one that simply issues an IO and waits for it to be done. How long does it take for complete both processes? Use dash C and dash P to find out if you are right. So this should take. We haven't mentioned what each IO should take, right? We read the label. I'm already forgetting stuff. Like cool. IO behavior. Yeah, dash L is the length. Okay, cool. So this should run synchronously, uh, where they will take a total of 4 and 1 5 instructions. So that's what this should take. Just got to do this. Dash A 400 and then 1 0. Right? 400 and 1 0. It was busy 5 and I was busy 4. Wait, what? Yeah. Process 0 goes CPU, 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 IO. And if I want to just add the dash C flag, it's okay. Process ID 0, process ID 1, CPU IOS. It's not proper table, fine, that's fine. CPU process 0, I assume is ready, 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 ready. Run IO, waiting, 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 waiting. But why did it wait for 5? That's what I'm thinking. Waiting, waiting, waiting. Cool. 4 instructions. Is it because of 4? Or is it waiting? So doing process yes, analyzing by 3, the equivalent is this. Cool. See, this is the kind of stuff that AI is for. Okay, so process ID 0. So CPU running. The process one is running, and then we run IO, and then we wait for 4 seconds. But where did we mention that it's going to wait for 4 seconds? I did not know about that. So, those are not like it's a one zero, no, tough, cool. Switch the order of the process 10400. Okay, let's try that. So, what should happen now? Well, I still think it will be the same thing because we haven't told it, right? We automatically takes like the default is the dash dash process later wherever the flag was. Right, okay, run IO ready, boom, waiting, and then you can do the stuff and that's just fine. Run the dash P so we get the stats. The total time is 6, and in the case above, total time is 10. Cool. We'll now explore some of the other flags. One important flag is dash S, yeah, which determines how the system reacts when a process issues an IO. With the flag set to switch on end, the system will not switch to another process while one is doing IO. Instead, waiting until the process is completely finished. What happens when you run the process when the following two processes 10400 C S switch on end? Dash C S 10400 dash S switch on end. This is capital S. Yep. It's a total of 9 because we cannot let other processes run while the other is doing its stuff. Now with the process but with the switching behavior set to switch on IO, which is the default one, I think. Yeah, same. We can only take 10, 10 is for done. Okay, good. Because we did not have a done over here. What happens now? Use dash C and dash P to confirm that you're right. One other important behavior is what to do when an IO completes. With dash IO run later when an IO completes the process that issued it is not necessarily run right away. Rather, whatever was running at the time keeps running. What happens when you run the combination of the process this? Uh, okay, so 3-0. Three instructions, sorry, three process. But what with the, I don't get it. Is it four by default? So we have one, two, three process which should be running purely on CPU, and there is nothing I related except the first one, which is 3-0. So uh, there will be one process which should have three lines. Yeah, three instructions, three processes. Wait, that's not lines. That's That's just three processes. Which I this. I can see it takes. Wait, let me confirm. Oh my God, I'm so dumb. Well, X is the number of instructions that process should run, and Y is this. Yep, okay. IO length is dash L. IO takes, and we are not mentioning dash L anywhere. It's a small dash L, which is just okay. IO run later. Oh, okay. So what's happening is that process one run IO and it goes into waiting, and in that time process one takes over. Run. And this is ready, and then this just keeps waiting until the last time. Run. Okay, so this takes a total of 27. Yeah. If we were to say like IO run immediate, it will go like if it's ready, boom. Like if it's ready, boom, give the control again. It should take a lot less time. Right, 18. So when IO is done, they are all ready. And this is waiting again. Boom, cool. Why might running a process that just completes an IO again for a good idea? Cool. Now run with some randomly generated process using flags dash s1 s dash s seed random seed. Okay. Dash l 350 or this. See if you can predict how the trace will turn out. What happens when when you use the flag dash I? Yeah, okay. Dash S seed. What does seed play? What role does a random seed play to decide whether each instruction is CPU or IO? Okay. Um, okay. I don't really get it, but okay, that's fine. I'll run it a bunch of times and then okay. Dash S1 means it's fixed. So 350, there are three lines of instruction. There are 350. Then it will be IO and is what about IO or CPU, IO or CPU. In this case, run CPU ready, run IO ready. Waiting, run CPU this. Cool. There are three steps, and one of them became CPU because it was 50-50, and 50-50 of 3 is 1.5, so you just choose it as 1, I think. If you were to do S2, random series 2, 350, for the same thing, you would get, okay, so run IO, this is ready, this is waiting, and then it's run CPU. Okay, what if I were to do 3? Okay, so which one is the most efficient one? We don't know. Let's check that. Okay, so roll time is 12, this is 13, this is 13 again. This moves faster because we ran the CPU and it's ready, done. In this case, we run this is taking the block of work. We run out. This is 350, the second process, 350. Where all the processes are CPU. So it was faster here. Two of them are IO, and here same thing, two of them are IO. Yep, okay. If we do switch on here, so if for S1, so for S1 we have two IOs, right? Right. Oh, okay. Yeah. I mean, I get what we are trying to do. That's it. So I guess it's done. I understand some of the stuff. I understand. cool things now. Cool. And I need to sleep. That's what I'm listening. So, 1 hour 41 minutes. So that's crazy. I guess thanks for watching this video. Yep. So, yep, I'll read about my stuff tomorrow, which I talked about. Stack pointer, frame pointer. It is at the end of the second page. And then on the third page, miscellaneous control. I should just I have shortcuts for this. Where does parent process create address space for child? I think my assumption is that it creates within the address space of the parent, but I need to check because that's what makes the most sense. Because if okay, no, I'm not going to discuss. Okay, I have my own theories. I think parent address space makes sense, but then there are other problems, so I'll think about them later. I'll think about it and then I will check whether I'm correct or not. If I'm not in my, I'm not. I'll just let you know in the next video. So thanks for watching this video. I'm Aditya Vashadni and I am an engineer for fun. Bye.